In our previous lecture, we created a data structure where we have 3 blocks. If you recall, for our previous hash for our blocks, we just had random strings stored. In our main function, when we created create block, we used random words like hash1 and hash2. In this lecture, let's implement the hash. And before we get into writing the code, let's go over a couple things. This is Go's document page, and we have here a section for packages. Under packages, we can research about the source files in the directory. Under packages, we have SHA-256. This time, we want to use the hash algorithm for SHA-256. Let's look at this package, and we have examples here, and even within examples, we have this list and an item called sum256. Let's use this sum256. Looking at this example may make this easier to understand. And what we're doing here is with import, we're importing crypto/SHA-256. Then here we have SHA-256, sum256. In this byte array, we store hello world to create our sum. And when we run this, then we get the following hash string. So what are we doing here? We have this byte array of hello world. We're using SHA-256 to create our hash. This may be difficult to understand, so let me printf and %v to show the content as is. Let's include new line here, then sum. We'll include new line here as well. When we run this code, we see in the upper section our byte array. We're using %x here and printing it in hexadecimal number. We'll be using this as our hash. I'm going to delete these rows, and now we're going to copy these 2 lines and paste it down below. And now we're going to make this sum2. Sum2 here as well. Let's run this one more time, and when we do, we see our hash on the top and bottom are identical. When we have identical strings like this, our program will display identical hashes. For example, let's change our first string to hello world 1. When we run our program with this, we see that our results for the top line changed. Now let's change this back to hello world, and when we run our code, our results displays the hash from before. This isn't a code, so you won't be able to decrypt and try to come up with this hello world. This is one characteristic of a hash. That means we have the data stored in this block. Using the data from this block, we create a hash and store this data in our next block. That's what we'll be doing in our next step. Now that we have a basic understanding of what needs to be done, let's go back to writing our code. We're going to scroll all the way to the top. If you recall, we created a type named block and created a structure. And now we'll add on to this to create our hash function. First, we'll write funcBlock. And this is a method, so we'll add hash here. The return value is 32 byte. Let's go back to our document to make sure we have the correct format and byte size. This is our document, and we'll click on example. And here we see func sum256. We see the returning size and byte. We'll click on size, and here we see const size equals 32. Now going back to our code, we just confirmed that we did correctly input the byte size. Let me explain the process of how this will work. First, we encode this information by JSON marshalling to make it SHA-256. So how can we do this? This is what we marshaled, followed by JSON marshal. This is followed by B for itself. And we'll return SHA-256, then sum256, followed by byte M. What this does is for this, we're making this into a JSON formatted string. Then just like in the example, we'll store what we marshaled into JSON and return our hash. And there's a problem with this, which I'd like to discuss. To make it easier to see, let's print M here. Let's scroll all the way down to our main function section. And let's call the hash that we just created, so I'm going to comment out these lines. Here we'll say block and create our block. Let's just say nonce1. In our next line, we'll write fmt printf and %x. Then block hash. Let's run our code with this, and when we do, we see this as a result for our hash. we get the results 44136 and so on. This is what we did with Jason Marshall. This is the byte. This will be easier to understand with a text string, so let's go back to our println and add string here. And now with this, let's run our code one more time. When we do, we get an empty set of brackets. Let's scroll up to our code and look at this block. We notice that all of these private fields are in lowercase. Therefore, when we marshaled, our results weren't transformed into JSON format. To solve this, we need to customize and execute JSON marshalling. This may be a little difficult to understand, but let me try to explain it. This is something that may be covered in an intro course, so it may be reviewed for some. We'll first write func_b block and then marshal JSON so that we can replace our method. This method will be one that will return byte as error, and in our next line, we'll return JSON marshal. We'll be writing our own struct, and for this, we'll write timestamp, but with a capital T. Then we'll define it as int 64. The same goes for our nonce. We have a capital N, and for previous hash, a capital P and capital H. We'll start off with capital letters, and same with transactions. Then we'll store B timestamp into timestamp, and B nonce into nonce, B previous hash into previous hash, and then B transactions into transactions. Now that we've gotten this far, let's run our code again. And this time, instead of an empty map, we actually do return results with values. And going one step further with this map, later on we want to use this information with our network. So to do this, we'll scroll up, and here we want to write JSON for when we're marshalling. For example, what type of timestamp do we want? For this, let's say we want our timestamp to be presented in lowercase. For our nonce, too, let's write JSON and lowercase nonce. For our previous hash, we'll write JSON, then previous hash in lowercase and with an underscore. This is how we indicate how we want marshalling to be completed. And the same goes for transactions. We'll write transactions with a lowercase t. Now that we've gotten this far, let's run our code again with this. And when we do this time, we see that our return values are printed in lowercase. Our block here is converted into JSON format, and then this is converted into a hash. These hash values are expressed as 16 characters of antilogs. Now let's refer to our code above. The byte size for SHA-256 is 32. So previous hash, we have been using string, but we need to change it to 32 byte. For this line here with previous hash and string, we'll change the string to 32 byte. Same for this line, we'll change the string to 32 byte. And let's scroll down below this string for previous hash. We'll change this to 32 byte as well. And for here, no changes needed for this previous hash line. Now let's look at our line with print and previous hash. We are printing strings, so we had S here, but we'll change this to X. And going down below again, for our line with new block, we have previous hash here, and it's returning error. We'll need to change this to string to 32 byte. And going up to this init hash, we'll store block and an empty map in B. Then we'll change this init hash here to B hash for our initial setting. I've rewritten many parts, so if you think you may have made a mistake along the way, please refer to the downloadable source code that's provided in this course. We've completed up to this point of creating a hash. Next, when we add on our new block, we need to add on our previous hash to this block. We link the blocks with a chain, but let's say we have this one block. Then this block can be referred to as the last block. And next, let's say we have two blocks. The last block, when we have two blocks, would be this second one. We want to include the hash for this block into our last block when we have three blocks. By adding on a method identifying what block is the last block will be helpful, so let's work on that from now. For this method, we'll write funcBC blockchain. in this blockchain, what is our last block? That's what we want to identify using this method. So write return BC chain. We want to refer to the last block in our chain, so we'll write BC chain length -1. After we've gotten this far, I want to go back to our main function. First, I'll delete these first 2 lines here. And in this new blockchain, we created new blockchain with the first 2 lines. Then we created hash1, where we have a string. We'll include previous hash and store blockchain last block's hash here. Then we'll look at our next line. We'll rename our hash1 to previous hash. I'm going to copy this line and use this line one more time. This time we'll make this equal and rewrite hash2 to previous hash. We have our first 2 lines here, and this refers to the very first block. This blockchain last block hash is stored in previous hash. We store this into our previous hash for our next block, meaning when we created this block, we included our previous hash. Then again, we have the same line where we take the hash from this block into our previous hash for our last block. And at the end, we'll print our blockchain. Let's run our code with this. This is our results. We have our chain 0 showing up here at the very top. We have, for our previous hash, the hash for our empty map from our initial setting. Then, next we have chain 1. The previous hash here is a result of our hashing our first block. Last, we have chain 2, and the previous hash for this is based on our data from our previous hash. With this, we've completed creating the hash portion for our blocks. As you see here, hashing links each block to its predecessor, making the data in the blockchain immutable. The codes are getting more difficult, so if you do find yourself confused or need more review, please refer to the downloadable source code that's provided and run the program based off of that.